The big and small problem number 3 revisits our bowling ball and golf ball that are both undergoing pure translational motion. As they begin moving, they have the same initial non-zero linear momentum. And as they move, we're going to apply the same constant net force to both balls. Those forces are going to oppose the motion of each ball. And over time and distance, that constant net force is going to cause each ball to come to a stop. The question we want to address in this problem is which ball travels further before it comes to a stop? Will it be the bowling ball or the golf ball, or perhaps they travel the same distance? And if you recall, in big and small problem number 2, we had the exact same conditions on both balls, but we asked the question, which ball requires more time to come to a stop? And the answer to that question was they both require the same amount of time. So with that in mind, I might think initially, well, perhaps if they take the same amount of time to stop, maybe they travel the same distance before they stop. So let's think about this. When we see keywords like travels further, what I want to do is think in terms of maybe distance or displacement that a moving object undergoes. But before we get into that, let's just revisit some of the information that we have that was found in the big and small problem number 2. We know both balls have the exact same initial non-zero linear momentum. And we also know that both balls are going to be influenced by the same constant net force that opposes the motion of each ball. And we also know that both balls come to a stop at the end of their motion such that their final velocities are both 0 and their final linear momentum values are both 0. So when I see the keywords travels further and I start thinking about distance traveled or maybe displacement undergone, I think to myself, well, the work energy theorem involves quantities that relate displacement and distance to the physics that's going on. And so let's investigate the work energy theorem in this particular situation. The term on the left-hand side of the work energy theorem, the total work done by external forces that act on our system, can be analyzed rather quickly if we consider one of the balls being our system. Either ball, the bowling ball or the golf ball, the only force that will do work is that force that acts on the ball that causes it to slow down. So if we call that force the net average force that acts on our system, the system being one of the balls, and if we assume the ball is going to travel along a path that is directed along an x-coordinate axis, if I assume that the ball is moving in the positive x direction, then this force is going to be directed parallel to the x-axis, as the I hat unit vector indicates, but it's also going to be in the opposite direction of the ball's motion. So minus this net average force that acts on the ball along the x-axis is going to be dotted with that differential displacement vector that describes how the ball travels along the x-axis as the ball begins at some initial position x sub I and it finishes up at some final position x sub s. This is an easy integral to evaluate because the net force is constant, and when I take the dot product of these two I hat unit vectors with each other, I'll get 1. So the total work done by that net force is just the value of that net force multiplied by what I'm going to call the delta x associated with the system, the delta x being the final position value of the ball minus the initial position value, xf minus xi. That's going to be the total work done on the system, one of the balls, and notice that work is going to be negative because we've got a minus sign here. The magnitude of this force is positive, and delta x is going to be an xf minus x initial, and if my positive x-axis is to the right, xf minus xi is going to be a positive quantity. So this work done by this force is going to decrease the energy of our system and cause the ball to come to a stop. The change in the energy of the system is only going to be due to translational kinetic energy changes because we're told that both balls are undergoing purely translational motion. And if I write my kinetic energy change in terms of my system's final kinetic energy minus its initial kinetic energy, and I use the expression for kinetic energy that involves the linear momentum magnitude squared divided by twice the mass instead of 1/2 mv squared, then this first term is going to go to 0 because I know both balls come to a rest when they're fully stopped. Their final velocities, their final speeds, their final linear momentum values are 0. And the total change in the energy of our system is just going to be related to how much initial linear momentum the system has and the mass. So knowing the expression for work and knowing the expression for the change in the energy of the system, we can write down our work energy equation again, and then write down the work expression that we got and the change in energy expression that we got. And by solving that equation for delta x of the system, we're going to find out that that change in position is related to the initial linear momentum of the system, the mass of the system, and the net average force that acts on the system. So we can wrap up by looking at the following types of relations. Both the bowling ball and the golf ball have the exact same values of their initial linear momentum. And so the P initial for both balls is going to be the same, as well as the P initial squared. The net average force that both balls experience is the same constant value. So this net average force is going to be the same for both balls. And we also know that the bowling ball has a larger mass than the golf ball. So the large mass bowling ball is going to have a smaller value of delta x than the golf ball that has a smaller mass that's going to undergo a larger delta x, a larger change in position. So what we find out is that the delta x for the bowling ball is smaller than the delta x for the golf ball. So which ball travels the longer distance is going to be the golf ball. The golf ball travels further than the bowling ball before it stops. And that might sound counterintuitive to what we got in the big and small problem number 2, where we found out that both balls required the same amount of time before they came to a stop. But the effects of forces over time and the effects of forces over displacements or distances are two totally physical effects, and those are wrapped up in both our impulse momentum theorem and our work energy theorem. So we're going to find out that both the golf ball and the bowling ball take the same amount of time to come to a stop under these conditions, but the golf ball travels a further distance over that time. Another area that's very interesting to look at involves the idea of bouncing. And we're going to study that through this problem right here, where we have a metal bullet and a rubber bullet that both have the same mass that are fired at a wooden log. And both bullets are going to have the same initial linear momentum, but when they strike the log, we're going to see that both bullets undergo two different types of behaviors or two different types of effects. The metal bullet is going to go through a portion of the log and come to a rest somewhere inside the log. But the rubber bullet, being an elastic material, is going to bounce off the outer surface of the log and ricochet back off in the direction that it originally came in. So the condition we're going to impose on this problem is that if the time interval for stopping the metal bullet inside the log and the time interval that it takes the rubber bullet to strike the log and turn around and reverse its direction back, if those two time intervals are the exact same, which bullet is more likely to knock the log over? And we can think of this in terms of maybe some type of impact force that each bullet is going to apply to the log and cause the log to fall over. So think about this, and we'll get back to you in the next video with the analysis and the solution.